Welcome to SS2 Physics, Term 3, Week 1. Electromagnetic induction is the principle that makes electric generators, transformers, and electric motors possible. Without it, there would be no electrical power grid. This discovery by Michael Faraday in 1831 changed the world. By the end of this lesson, you will state Faraday's law of electromagnetic induction, apply Lenz's law to determine the direction of induced currents, explain the operation of a simple AC generator, define flux and EMF, and solve WAEC-type problems. Let us begin. Before electromagnetic induction, we need the concept of magnetic flux. Magnetic flux, a Greek letter phi, symbol phi, is a measure of the quantity of magnetic field lines passing through a surface. Phi equals B times A times cos theta, where B equals magnetic flux density, in Tesla, T, A equals area of the surface, M2, theta equals angle between the magnetic field direction and the normal to the surface. When the field is perpendicular to the surface, theta equals 0 degrees, flux is maximum, phi equals BA. When the field is parallel to the surface, theta equals 90 degrees, flux is 0. Unit of magnetic flux, Weber, WB, 1 Weber equals 1 T M2. Faraday's law of electromagnetic induction, 1831. An EMF is induced in a conductor whenever there is a change in the magnetic flux linked with that conductor. The magnitude of the induced EMF, E, is directly proportional to the rate of change of magnetic flux. Mathematically, E equals N times delta phi slash delta T, where N equals number of turns of wire in the coil, delta phi slash delta T equals rate of change of flux, WB slash S. The negative sign indicates that the induced EMF opposes the change, Lenz's law. Practical implication: to induce an EMF in a coil of wire, we can move a magnet towards or away from the coil, move the coil towards or away from a magnet, rotate the coil in a magnetic field, change the strength of the magnetic field, e.g. by changing current in an electromagnet near the coil. The faster the change in flux, the greater the induced EMF. A stationary magnet near a stationary coil produces no EMF, there must be change. Lenz's law, 1834, Heinrich Lenz, describes the direction of the induced current. Lenz's law, the direction of the induced current is always such that it opposes the change in magnetic flux that caused it. This is consistent with the conservation of energy. If the induced current did not oppose the change, it would amplify itself without any external work being done, which would violate conservation of energy. Practical applications of Lenz's law: if a bar magnet is pushed towards a solenoid coil of wire connected to a galvanometer, the induced current creates a magnetic field that opposes the approaching magnet. The end of the solenoid facing the magnet becomes a north pole, which repels the approaching north pole of the magnet. Work must be done to push the magnet in against this repulsive force. This work becomes the electrical energy in the induced current. When the magnet is pulled away, the induced current reverses direction. The end of the solenoid becomes a south pole, attracting the retreating magnet, again opposing the change and requiring work to pull the magnet away. The right-hand rule helps find the current direction. Curl the right-hand fingers in the direction of current flow in the coil, the thumb points in the direction of the magnetic field produced by that current. Electromagnetic braking. Lenz's law explains why dropping a strong magnet through a metal tube causes it to fall much more slowly than expected. The changing flux induces currents, eddy currents, in the metal that create a magnetic field opposing the motion. Used in braking systems on trains, magnetic brakes, and in metal detectors. An AC, alternating current, generator converts mechanical energy into electrical energy using electromagnetic induction. Structure: a rectangular coil of wire, or ABCD, rotates in the magnetic field between the poles of a magnet. As the coil rotates, the magnetic flux through it changes continuously, inducing an alternating EMF. Two slip rings are attached to the ends of the coil. Carbon brushes maintain electrical contact with the slip rings as the coil rotates, allowing current to flow to the external circuit. How EMF varies with rotation. When the coil is in the vertical position, plane of coil parallel to magnetic field, field lines parallel to the coil plane, rate of change of flux is maximum, field lines cut at maximum rate, EMF is maximum, peak EMF is 0. When the coil is in the horizontal position, plane perpendicular to field, field lines perpendicular to coil face, flux is maximum but rate of change is 0, EMF equals 0. The EMF varies sinusoidally, E equals E0 times sin, omega t, where E0 equals peak EMF, or volts, omega equals angular frequency equals 2 pi f, rad/s, t equals time. Peak EMF, E0 equals mo equals NBA times 2 pi f, where n equals number of turns, B equals flux density, A equals area of coil, omega equals angular velocity. This sinusoidal variation explains why the power supply from generators, and from the national grid, is AC. The generators are simply rotating coils in magnetic fields. In Nigeria, the national grid frequency is 50 Hz. WAEC often tests calculation of peak EMF using E0 equals mo. Worked example 1. A coil of 200 turns and area 0.04 square meters rotates in a uniform magnetic field of flux density 0.5 T at a frequency of 50 Hz. Calculate A. The peak EMF. B. The EMF at T equals 0.002 S. Solution. A. E0 equals no equals mo equals n times B times A times 2 pi f is equal to 200 times 0.5 times 0.04 times 2 pi times 50 is equal to 200 times 0.5 times 0.04 times 314.2 is equal to 200 times 6.28 is equal to 1256 V. B. E equals E0 times sin, omega t, equals 1256 times sin, 2 pi times 50 by 0.002, equals 1256 times sin, 0.628 radians, equals 1256 times sin, 36 degrees, is equal to 1256 times 0.588 equals 738.5 V. Worked example 2. The flux through a coil of 100 turns changes uniformly from 0.2 webers to 0.05 webers in 0.5 seconds. Calculate the induced EMF. Solution. E equals n times delta phi slash delta t equals 100 times open parenthesis 0.2 minus 0.05 close parenthesis divided by 0.5 is equal to 100 times 0.15 divided by 0.5 is equal to 100 times 0.3 is equal to 30 V. WAEC question patterns on electromagnetic induction. State Faraday's law. State Lenz's law and give an example. Calculate induced EMF from change in flux. E equals n times delta phi slash delta t. Calculate peak EMF of a generator. E0 equals mo. Explain why the induced EMF in a rotating coil is alternating. Describe the structure and operation of an AC generator. Explain eddy currents and their applications. Induction heating, breaking, and disadvantages. Heating losses in transformer cores, minimized by using laminated cores. Key points. Magnetic flux phi equals BA cos theta, measured in webers, WB. Faraday's law, induced EMF equals n times delta phi slash delta t, EMF is induced whenever flux changes. Lenz's law, induced current opposes the change that caused it, consistent with conservation of energy. AC generator, rotating coil in magnetic field, EMF equals E0 sin, omega t, peak EMF E0 equals mo, slip rings and brushes transfer current. EMF is maximum when coil is parallel to field, maximum rate of flux change, 0 when coil is perpendicular to field, flux is maximum but not changing. Eddy currents, induced in solid conductors in changing magnetic fields, cause heating losses in motors and transformers, minimized by laminated cores, used in induction cookers, electromagnetic brakes, metal detectors.